Okay, good afternoon. So we have been looking at different ways we might represent text. And depending on the medium that you're using, you might have a number of different slots. And we considered how you might best use those slots. And when the number of slots was constrained, we talked about having escape sequences and stuff to double up things. When you're representing numbers using bits and you have 7 bits, you can have up to 128 different characters. And that turns out to be plenty for most purposes, because you have your uppercase and your lowercase. How many am I using here? 1, 2, 3, 4, 5, 6, 7. Okay. I've expected a bit more. Oh yeah, I'm not using all the slots here. But with 7 bits, you have up to 128 different things. So that's plenty. However, if someone just says to you, 0, 1, 1, 0, 0, 1, 1, that doesn't mean anything. Okay, you can convert it to a number if you want, but then all you have is a number. It doesn't mean anything. The mappings of bit sequences are the mappings of numbers to letters must be shared between the transmitter and the receiver. So in order to decode a sequence of bits, the table that maps them to the characters, to the letters, has to be available. Without that, all you have is a bunch of bits that could mean anything. So, quite some time ago, people agreed on standards for mapping letters to numbers. And the most popular one was the American Standard Code for Information Interchange, or ASCII. There was another one, ASCII, which was used by IBM. IBM was very big, so you couldn't ignore it. But we don't use ASCII anymore. And so ASCII is the main way we map code to, the main way we code text. The main way we map letters to numbers, and then from numbers in turn into bit sequences. Okay? And so ASCII uses 7 bits for each character. So in 7 bits, you can have values from 0 to 127. So 0, 0, 0, 0, 0, 0, 0 is 0. And 1, 1, 1, 1, 1, 1, 1 is 127. Okay? And that was hunky-dory for a long time. Now, the problem is that as the American Standard Code for Information Interchange, this was devised by English speakers who didn't quite imagine a world where you would have characters other than the English characters. So there's no acute E, for example, or an E fada, as we might call it. There's no sharp S that you might need in German for a word like Strasse. That's a bad example because you don't know which of the S sounds I'm talking about, but anyway. And there's no ñ character in that. So when you say the difference between España and España is that squiggle over the N. Spanish people would consider this to be a different letter because of that squiggle. So this was a problem where non-English characters are required. If we just have a look here at an ASCII table from, this looks like quite old. So, oops. So these are the most significant bits here, okay? So uppercase A is this slot here. So the bit sequence for that is 1 0 0 0 0 0 1. What's 1 0 0 0 0 0 1? What's that in decimal? So you shouldn't even have to think, because most of you know what uppercase. Well, any takers? 65. And that shouldn't come as a huge, well, that uppercase A is 65. Most of you maybe already know that. So in many programming languages, you for various reasons, you might want to convert from the character to the number that represents it. So uppercase A has an ASCII value of 65. Lowercase a, on the other hand, is 1 1 0 0 0 0 1. What's 1 1 0 0 0 0 1? 97. And that's the ASCII value of lowercase a. You might ask why lowercase a, if they're putting the letters after the lowercase letters after the uppercase letters, they didn't just go to Z and then start A, B, C, D straight after that. So that it'd be 26 off. But by having them 32 values off, the difference between an uppercase letter and a lowercase letter is actually just 1 bit in the difference. Or is it more than 1 bit? Yeah, so this second bit here, an uppercase letter. So an uppercase E is 1 0 0 and 0 1 0 1, and lowercase e is just 1 1 0 0 1 0 1. So between the uppercase letter and the lowercase letter, there's only 1 bit of a difference. So you could imagine there might be some bit twiddling party tricks you might be able to do there if you wanted. Down here at the lower end of the table, now this is very old. So down here at the lower end of the table, there's a whole bunch of stuff, like we'd call them control characters or control sequences. So this here is acknowledge. This might be synchronize. Many of these are lost to the, sands of time. I'm sure there's plenty of people out there know what they are. This CR is probably for carriage return. So when you were sending to the printer, it would go on to the next line. Things like that. So if you have a text file and you're sending it to the printer, there would be a character that says, go on to a new line. This bell here, programmers have great fun with the bell, because if you write out character number 7, the machine will go bing, because bell was literally a bell or a beep. So you can sometimes, for the crack, output a sequence of characters, and if you somehow output character number 7, you'll actually make the machine make a noise just by sending it some text. Okay? So in 7 bits, we go from 0 to 127. You notice in there, no accents, no fathers, no enyas. It's constrained enough. At the same time, it's a perfectly fine character set for English. So on this one, uppercase C is 1 0 0 0 0 1 1. So depending on the table, you sometimes read these ones first and then these ones, or these ones and then these ones. bit 7 here, the bit that represents the largest value, the one on the left, that's called the most significant bit. And the rightmost bit that represents the 1, that's called the least significant bit. And when you look at a table like this first, the confusing thing is, is this the most significant bit, or is it this one? In the table I showed you here, see, it goes a different way. But you notice I'm doing A, B, C, D across rather than down as well. Okay, so with this ASCII table at the sender and the receiver, you could send 7 bits at a time. You could send your message. And not forgetting, of course, 32.010.0000 was the space. Every computer nerd knows the ASCII value for space, uppercase A and lowercase a, and maybe the start of the numbers as well. Now, so that was fine, and that was grand for a long time. But what happened then when you went to Spain or to Germany? Clearly, people in those countries needed a bit more than just the plain vanilla English characters. So ASCII was extended. So in the positions from 128 to 255. So if you have like an 8-bit ASCII, if the first bit is 0, then you're talking about 0 to 127. That's standard ASCII. But then from 128 to 255, when the first bit is 1, well, then that's not standard. And that worked fine for many, many years. So if you were in Germany, the English characters were 0 to 127. You had your German characters floating around there somewhere between 128 and 255. If you were in Portugal or Brazil, you had the regular letters 0 to 127, and from 128 to 255, that's where your Portuguese characters were living. Similarly in the Spanish-speaking world, and so on. Once communication systems started to communicate across national boundaries, then you did start to have problems. So sometimes you might get an email from France or a text message in French, and it doesn't quite work. If someone puts a cute over a letter E, it might, freak out a bit. That can happen from time to time. So standard ASCII occupied the positions from 0 to 127, and then from 128 to 255, well, all bets are off. Depending on where you are in the world, character number 200 might be any number of things. And so country by country, people, gave it a lash like. So you had these things called 8-bit DOS code pages. So like code page 337 was for Greek. And in that, in position 0 to 127 was regular standard ASCII, but 128 to 255 Greek stuff. You had, CP 850, Latin 1, Western European languages. Again, 0 to 127, standard ASCII, 128 to 255, all the French, Spanish, Portuguese stuff is probably thrown in there. You can see there's a whole bunch of them. Look, Portuguese got its own one, Icelandic got its own one, Hebrew had its own one. French, Canadian French got its own one separate to French. The mind boggles, There was one for Nordic languages. there was Cyrillic ones. Even with the Cyrillic ones, there might have been a different one in Yugoslavia to the one used in Moscow. I was tempted to say Russia, but it probably wasn't Russia. If you had Yugoslavia, you probably didn't have Russia yet, really, as a single entity. So if you were in the English-speaking world, you were oblivious to all this, because you were still only doing stuff 0 to 127. You were only using that part of the table, and it's all the freaky stuff was going on somewhere else. So if something was coded in CP860 in Portuguese, but you were in Iceland opening the file expecting it to be in CP861, then some of the Portuguese characters might have been interpreted as Icelandic characters, and things went wrong. But we in the English-speaking world were happy out. Okay. Eventually, these became standardized, because these were even a bit makey-uppy, Eventually, they became standardized as ISO standards, International Standards Organization. So you had things like ISO 88591, ISO 88592, and things like that. Your Arabic was an ISO 88596. There was one for the Baltic languages plus Polish. You needed a different one for Irish. They're calling it Irish Gaelic there on that list. So even in Ireland, you could conceivably have had documents in ISO 88591 and other documents in 88514 if someone had the gall to actually write in Irish, God forbid. But at least these were standards, and at least you knew what you were getting. And very often, maybe at the start of a document, there might have been a little header that said, this is an ISO 8859-5 document. So at least the system knew what it was supposed to do or something. Okay? But you can imagine it was a bit of a head wreck. You are working in a big computer company. You are given a whole bunch of records to put into a database. They come as text documents, and you have to figure out, okay, so this is in ISO 8859-3. But I was our system only deals with ISO 8859-1. Now this kind of carry on. Okay? Vietnamese was a particularly interesting problem, because to write Vietnamese you needed 134 slots. So like the Portuguese and the French and the Spanish and even Hebrew, they were happy enough they could fit in all their business here between 128 and 255. But Vietnamese needed 134. So there were a number of possible options they could have gone for. And instead what they did was they actually robbed some of, if we go back here to these control characters here that kind of aren't used anymore. They looked at those and said, which are the really, really useless ones? The ones that are hardly ever used at all. And so they robbed a few of those. So if you were expecting a standard ASCII document and it had Vietnamese in it, there was a slight chance that if you sent it to like a really old printer or something, it might go bananas. One of these might have been the self-destruct sequence or something. But for the most part, it didn't really cause a problem, because those things at this end of the ASCII table were kind of not really used that much anymore anyway. But it was certainly like a head wreck. I'm sure people are saying, these feckin' foreigners and all their foreign stuff, if only everyone in the world spoke English, we'd be grand. But that wasn't a solution either. But it's certainly unfortunate that when ASCII was devised, it didn't include, I mean, the notion that you would call it the American Standard Code for Information Interchange and not accommodate Spanish was certainly mental. Even if it was the US Standard Code for Information Interchange, you'd still wonder why it didn't dawn on them that there might be some Spanish speakers in the US once upon a time in the future. Okay? Just as an aside, SMS uses a 7-bit code. So when you send a text message, each character takes 7 bits. And there's actually some maths you can do which explains why it has to be 140 characters or less then. When you consider it's 7 bits per character, 140 characters falls out of that eventually. Is it on 640? Can't remember. Can you send 160 characters or 140 characters? Oh, that was 140. I don't know. You can see. And so needless to say, it doesn't accommodate any of the foreign stuff. So if you get a text message from France with some accents in it, it might screw up, or as we can see, something else might happen. So people did, there are like national profiles where you can be pretty sure everyone within France sending messages is using the same system. But when you cross borders, it can get a bit messy. So if you send a French message to a Spanish network, things can go a bit screwy. Which is why then, for non-English characters, it switches to a thing called UCS2. The details of which aren't important, but then that uses 2 bytes per character. So UCS2 can accommodate a much wider variety of characters, but of course you can still only fit the same number of data into the text message. You've still only got a fixed number of bits. So then it basically halves the number of characters you can send. And this has turned out to be a big problem for some Irish people. So you have situations where a Gael skull wants to send a message to all the parents. I won't embarrass myself by imagining what that message might be, as Gaeilge. But if the message contains a father, well then there's a very good chance that the system you're using will switch to UCS2. But if they're used to sending messages that are 140 characters long, it ends up taking 2 text messages instead of 1. And so then the phone company or the message servicing system charges them twice as much. And so they have people giving out that, you know, Irish speakers are being discriminated against because it costs them twice as much to send their text messages as English speakers. But that's because it doesn't fit in to the 7-bit code. So if you're going to have an extended character set, you need more than the 7 bits. And if there's a single, it's not that like it does it for each individual character. A single father in the message would cause the entire message to be transmitted using UCS2 instead. And so that's a bit of a problem. So I'll put a link there on the blog to a newspaper article giving out about that. No. So to solve all of these problems, a bunch of people got together and came up with, or started work on, Unicode. And so Unicode is sort of like a UN almost coding system whereby this one system will code all of the world's written languages. And it's fairly comprehensive. I mean, it includes the obvious ones, you know, Chinese, Japanese, English, Korean, Vietnamese, whatever you haven't. But even quite old writing systems. There's some ancient writing systems that we found and we don't even know what they mean. And Unicode can account for those. It does Ohm, for example. Ohm is a very old Irish writing system using marks, typically on stone. And so there's, you know, Unicode can accommodate those. It's fairly comprehensive and tries to include pretty much all of the languages used. But there was some debate, all right. Some things were left out. So there was an awful lot of discussion about whether Klingon should be included or not. And Klingon is not included in Unicode. But it was a close call. It's that comprehensive. Okay? So Unicode specifies code points, they're called. And there is a subtle distinction between the code points and the, you know, bit sequences. So uppercase A will have the code point 65 in Unicode, and lowercase a will have the code point 97 in Unicode, which is fair enough, like. And from this, the code points 0 to 127 match perfectly to ASCII. So a space has code point 32. Now in ASCII, going from 65 to 7 bits is trivial. And in 8-bit ASCII, going from 65 to 8 bits is trivial. But it turns out when you get up to code point 32,419, there may be other ways of doing it. Okay? So you can imagine Unicode as a huge, mega ASCII type table that goes up to, I don't know how many million, whatever. At the bottom of that table, or at the top, depending on how you look at it, at the top of that table where you have, like, you know, 0 to 127, that's familiar territory for us. That's the ASCII stuff we've been using since, you know, the 1960s. So the first chunk of Unicode is ASCII. But then it goes up to, you know, 16 million, whatever. So, you know, character number 16,275,000 might be some Chinese character. I'm quite sure, actually, that a lecturer giving this class in China would be able to tell you exactly where the Chinese characters start in Unicode. Just as I could tell you that A starts at 60, you know, uppercase A is 65. I'm sure he'd know that. And I'm sure a lecturer giving the same class in Japan would know exactly where the, you know, the Japanese character starts, but I don't. But you just imagine it as a humongous table. But how we code 16,375,000 using bits isn't necessarily the same way we would have coded 65. Okay? So there's a couple of different things. So the mechanism for encoding Unicode in bits can vary. All that's fixed are the code points. So we can say that this Chinese character here has a particular code point. 16,000,002 or something. Okay? So, one way you can save text is UTF-7. And that's basically 7 bits per character. Now, that's not actually part of Unicode at all. Okay? So this isn't one of the ways you can save Unicode. But it is worth a mention because we often see it used in email systems. So if you get an email from France and the accented characters are screwed up, that's because your email system was expecting email in UTF-7 when in fact it was something else. So I just mentioned this because it's still around. People still use it. And as we saw in text messages, 7-bit systems are still in use. Now, I'm jumping now straight ahead to UTF-32. And so UTF-32 uses exactly 32 bits per character. Did I bring my phone? No. And 2 to the power of 32 is a lot. So you can code an awful lot of code points in 32 bits. And I think initially the plan was that everybody would code everything in UTF-32. So when you open up a document, English, Chinese, Japanese, Korean, the Spanish characters, they were all in there, no problem. 32 bits per character, 32 bits is the new 8 bits. And that, that was quite sensible and had a good chance of working. But the only thing is that it meant that in the English-speaking world, where everything we did, and even if you take, say, English-speaking and, Western European and even, Poland, by the time you included, say, all of Europe and Latin America, you could probably represented everything they did in 1 byte. They might have everything they needed. And so people in the Western world were kind of, well, yeah, that's, that's great, like 32 bits per character, yeah, and everything we'll all be using the same system. But like that means every single thing we do would be 4 times as big. So now my email will, take 4 times as long to get where it's going. My text documents will be 4 times bigger. My ebooks will take 4 times as long to download.
HTML is mostly ASCII.
Yeah, my HTML file, my web pages are going to take 4 times as long to download. It's great for you people speaking Chinese and Japanese and stuff like, but I mean, feck off, like. There's no way we're going to make everything 4 times bigger just to accommodate, foreigners, like, doing their funny writing. So it's possible to code Unicode using UTF-32, but it's not terribly popular. Okay? There's another one then, which is UTF-16, which uses 1 or 2 16-bit units. So each character might be 2 bytes or 4 bytes, depending. And here we're starting to see a variable length code. So if you were using UTF-16 and your document was entirely in English, I'm going out on a limb here now because I don't actually know this, but I suspect that you would have just used 2 bytes per character. And it's only if you went into Japanese or whatever that you might trigger the 32 bits or the 4 bytes. I looked into the details of UTF-16 and how it translates to bits, and I just ran away. Okay? Now, UTF-8 is probably the most popular scheme that we have. And despite what the name might suggest, it doesn't use 8 bits per code point. It uses 1 to 6 bytes per code point. No, actually, that's not true. It's really only 1 to 4. Okay? And it can code all the Unicode code points. But the most important thing about it is that it doesn't piss off the English speakers. Because if you use UTF-8 to code a document in English, it only uses 1 byte per character anyway. So we use UTF-8 a lot now. So basically, if the document is in English, it's like bog standard ASCII. If you switch to French or Greek, you're probably hitting 2 bytes per some characters. You know, only the freaky ones need the 2 bytes. And then if you throw in some Japanese and Korean, well, you might be up to, 3 bytes or 4 bytes. But the length of the code required for the character varies with the characters. And like I said, the trick is it keeps the English speakers happy because, they can accommodate this without making everything 4 times bigger than it needs to be. It's a bit tricky though. It's a bit clever as well. So hopefully in admiring the cleverness of it, you'll get past the trickiness of it. So, when we're in the ASCII part of the table, 0 to 127, the first bit of the byte is 0. And then you go from 0 to 127 with the remaining 7 bits. Which is kind of what you do anyway. So if a document is coded in UTF-8, if an English language document is coded in UTF-8 and someone opens it up expecting plain vanilla bog standard ASCII, they won't get any surprises. And that's the key feature of it. Have to keep the English speakers happy.
Easier to update legacy systems.
Well, yes, in the English-speaking world. But yeah, there are a number of good reasons for that. So it's the super new mega modern system is completely compatible with ye ancient 1960s system. So you can open up something that's 40 years old and it'll look grand. More importantly, something that is 40 years old can open up a document and be able to deal with it. Okay? So here, the hexadecimal code point 20 or 32, which I said earlier was a space. So 32 in binary would be 0, 1, and then 0, 0, 0, 0, 0. Okay? So it's 0, 1, 0, 0, 0, 0, 0, and there's a 0 in front of that. So from 0 to 127, Unicode and ASCII map perfectly to each other. Now here's where the plot thickens. Once you go from 128 up, it gets a bit freaky. So what we have now is we have 2 bytes, okay? And here we're coding character number 512, whatever that would be. Who knows what that could be? It could be Greek or something. I don't know. Okay? And there are different bits Okay, so if we look here, 512 in binary is 0, 1, followed by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 512 in binary. That code, that sequence there of bits is broken up into two chunks. Okay, the last 6 bits, so the least significant 6 bits are the last 6 bits of the second byte. And these two here, these 2 bits here of the second byte are always 1, 0. And then the remaining bits fit into the first byte. And the first 3 bits of the first byte are always 1, 1, 0. Okay? So these bits here are a bit like metadata. They're not the information, they're stuff about the information. And then the payload is carried in these bits here. I might come back to this in a second, okay? So we call this first byte the leading byte, and the second byte is the continuation byte. And so if you get bytes, if you get a byte coming in and it starts with 1, 1, 0, well then you know it's the first of 2 bytes. And when the second byte comes in, it's always going to start with 1, 0. You know, okay, this is the continuation byte. The actual data then is spread across the 5 and 6 available bits that are left over. So the payload is 11 bits. So you have 16 bits to play with. You're only using 11 bits for data, and then you're using 5 bits for like kind of control. Gets more interesting. The next part of the table, the following code points then, they might require 3 bytes. And so here, the leading byte, if you look at the difference, this one was 110. Here the leading byte starts with 1110. And then the 2 continuation bytes start with 10. And then the payload is coded in the remaining bits, of which there are 6, 12, and 5, 17. So you've got up to this stage 2 to the power of 17 different things. So here, if we take the hex value B612, that's 46,610. So imagine now you have your super mega table with 65 is uppercase A, 64,610, I don't know, some Japanese character, say. On a normal day, 64,610 would be this bit sequence here, 10, 110, 11, blah, 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 blah. Okay? The last 6 bits go in here. This 1 0 is like a separator. The next 6 bits go here. We have this 1 0 marking that byte, and then the last 4 bits will go in here. Three ones here in the leading byte means that it's a 3-byte character, or 3-byte code point. So we'll carry on with that the next day, I think, because that needs a bit of time to sink in.